Hi, in this video we're going to continue our discussion about Chapter 12, Section 2, all about vectors. In this one in particular, we're going to talk about some applications of this. First, let's wrap up our discussion of direction. So, note, big note, any unit vector is on or touches the unit circle. Unit, get it? So if I have a unit circle, pretty good. It was going really good for a second, huh? If I have a unit circle, cool. And I have some sort of unit vector in there. It's going to be the picture as old as time. We have a unit vector in there. We could describe this unit vector by theta. So unit vectors. Oops. So unit vectors can be described by theta, by angles. How? So if that's my angle theta, I'm going to take this picture and blow it up. We have a unit vector u. We have the positive x-axis, right? And if this is theta, what's the opposite side? It'll be the sine of theta. And what's this side? What's the x-coordinate? The cosine of theta. So the unit vectors are all some angle theta plugged into cosine and some angle theta plugged into sine. Or in ij notation, cosine theta in the I direction plus sine theta in the j direction. Okay? How is this useful? How would we possibly use this? Example, find a vector v such that the length of v is 9 and the angle is pi over 4 from the x-axis. What's really powerful of this is it's not even that hard. The unit vector you would use is cosine pi over 4 I hat plus sine pi over 4 j hat. Now, we can talk about how we don't need to simplify everything always, but here we really should. Root 2 over 2 I plus root 2 over 2 j. And just like we did in the last example, now you can just scale that up. V would be 9 unit vector, or again, I'll just write it out this way, 9 cosine pi over 4 I hat plus 9 sine pi over 4 j hat. And I hope you can see how you go right to this. You could go right to this as long as you know the angle and the magnitude. So it'd be 9 root 2 over 2 I plus 9 root 2 over 2 j. Very straightforward questions, to be honest. What's not so straightforward is these applications. So if we have an example where I have 2 ropes holding a box, it's technically statics. Okay, they're holding the box unevenly. Kind of like a home improvement project I would do here. That's 30 degrees. Oh, look at us using degrees again. That's 60 degrees. So these are 2 ropes, and the box weighs 2 pounds. And the question is, find the tensions in the ropes, period. So if you don't know anything about physics, this might be a little confusing. I'm going to try to go over the basic physics you need to know. It's usually pretty straightforward. Idea. Okay, what is a weight? A weight is a force. And forces are vectors. So this blue vector here is W for the weight. So for instance, the weight vector, okay, this is W for weight, will be 2. And then what direction is it in? It's 2 in the down direction. So you could just use cosine 3 pi over 2 I hat plus sine 3 pi over 2 j hat. Sorry. So what's that simplify to? 2 times 0, 0 I hat is 0, minus j hat, or negative 2j. So basic idea, I guess I could write this overall. The idea here is that forces are vectors. Forces have direction. Forces have magnitude, size, strength. Okay? This vector, this box's weight, points down because gravity pulls us down. Gravity holds us down. You should be able to understand why you could just get negative 2j from just the picture without finding this angle. Okay, but that's idea number 1. There's that vector. Now the tensions are forces in the rope. Okay. We have 2 tensions to worry about. We're going to have tension 1 over here and tension 2 over here on the right. How are you able to find the tensions? If this body is at rest, we have a Newton's law of motion here. Newton's law of motion says that if we're at rest, the forces are balanced, right? If the object is not being accelerated, the forces must be equal, which is that basically W plus tension 1 plus tension 2 all have to be in perfect balance. And this is enough to solve the problem. Wait, how? Why? I hear you saying. Okay. So let's talk about tension 1. Tension 1 has a size, and then it has a direction. So notice how it has to point up, and to the left. Sorry. So what I want you to do is to draw axes here and just try to think about what angle that has to be if that's 30 degrees. If we have 30 degrees in that corner, what you should hopefully notice is that right there is also 30 degrees. Now, this doesn't sound that familiar to you. This is kind of a parallel angle theorem. Okay? If that's 30 up there, or you could use another parallel angle theorem to say this angle over here, let me just draw it, is therefore 150. So my T1, my vector T1 is the magnitude of T1 times cosine 150 in the I direction plus sine 150 degrees in the j direction. You should be able to do the same thing for T2. I'm going to give you a chance to work it out yourself. Please be careful. Please be careful. You want to get an axis from the positive x. Spoiler. So T2 would be the magnitude of it, which we don't know, just to be clear. I don't know the magnitude of T1, but I do know the angle. This is the same thing I'm going to say here. So you should try to draw some axes around it. And then you would notice, oh, this is still 60. 60 in the I direction plus sine 60 in the j direction. Honestly, for me, it's been so long, I forget how to do trig in degrees. So in real life, if this was an application, probably you could use a calculator. I'm not that interested in the calculator. I'm just going to try to do it without. We'll see. If you don't hear this part, it's because I edited it out. So this will be the magnitude of T1. Oops. 30 degrees. This is a small angle. So we're talking about cosine is root 3 over 2. But we're in the negative side. Plus sine is 1/2. Positive still. And for T2, we have 1/2 in the x direction and root 3 over 2 in the j direction. So everything I've done so far should make sense. You're breaking it up by the angles. We're finding the components of them. The components of everything is based on the angles and the magnitudes. We're trying to find the magnitudes of these forces in the ropes that are sharing the load of the weight. So now I'm going to plug everything in. W, so we're going back to this equation. W plus T1 plus T2, all the forces on this object have to add up to the zero, technically it's a zero vector. What does that mean? Negative 2j plus T1 negative root 3 over 2 I plus 1/2 j plus T2 1/2 I plus root 3 over 2 j. All that has to add up to 0. If that's true, it must be that the I components all add up to 0 and the j components all add up to 0. So what I'm really going to do here is try to add things up by their like terms. I'm going to add up all the I stuff and all the j stuff. I'm going to say that one more time. I'm adding the I stuff and the j stuff. So what I got here is there's no I component from the weight, from the W. We have T1 times root 3 over 2 negative plus 1/2 T2, and this is all in the I direction, plus minus 2 1/2 T1 plus root 3 over 2 T2 in the j direction still equals the 0 vector. I'm going to shrink this, and the 0 vector, for those of you who don't remember, is 0 in both components. So what can we do here? what we can do is say that therefore negative t1 root 3 over 2 plus 1/2 t2 equals 0. The I stuff and the j stuff. Negative 2 plus 1/2 t1 plus root 3 over 2 t2 equals 0. Solving this equation, you could get that t2 equals root 3 t1. And so this equation, you'd have negative 2 plus 1/2 t1 plus root 3 over 2 root 3 t1 equals 0. That's 1/2 t1. I'm going to add 2 to both sides. Plus 3/2 t1 equals 2. And if you solve that correctly, I think you would get t1 equals 1. Which means the magnitude of t2 is root 3. And those are the two sizes of the forces that are opposing that weight of 2 pounds. We have 1 pound pointing up into the left, root 3 pounds pointing up into the right. It's a lot of work. I'm not necessarily wanting to see all that for you. We might not assign you a problem like that, but you should know what to do if push came to shove. The other thing I want to look at, a much more easy example, one I would be interested in you solving by yourself, is to find a true course. Okay, so the idea is I have a plane flying. We'll say this is north. My plane is flying at an angle of 45 degrees away from north, careful. And my plane is directing with a force of a speed of 500 miles per hour. Okay? My wind is blowing in an easterly direction. Nope. My wind is blowing in an easterly direction such that the wind's speed is 80 miles per hour and the direction is actually 15 degrees. So they want you to find the true course, which is also known as the resultant. It would just be literally the vector p plus the vector w. They could ask you to find the ground speed, which would be the magnitude of the true course. How fast are you flying over the ground? And you could also find the actual heading. And the heading would be the unit vector in direction of p plus w, the true course. You should have a good idea of how to do this, especially if you just watched the rest. So I'm going to give you a chance, especially if you just watched me do the last example. So I'm going to give you a chance to try it. Please try it and come back when you're done. All right, so I've rearranged some stuff. If you had to watch a few more seconds of the video, sorry, it might be a jarring cut. So P would be 500. Did you find the right angle here? It should be cosine of 45 because the complementary angle is still 45 in the I hat direction, and sine 45 in the j hat direction. I guess I could have said this earlier. You could have used a calculator here if you're regretting your whole life and saying, "Oh man, I should have not listened to him. I should have watched more of the video first." I'm just going to tell you what the numbers are now anyway, so I don't know why you're whining. This would be 353.553 in the I hat direction plus 0.553 in the j hat direction, right? 45 degrees is the only one that's the same. The 15 degrees was the giveaway that you should have used the calculator, so I'm not going to take the blame for that. 80 times cosine 15 in the I hat direction, sine 15 in the j hat direction. So I'll say this, if you got those numbers the same, you messed up. This should be 77.274 in the I hat direction, and the sine should be smaller than that, plus 20.705 or 706 in the j hat direction. So how do you add these up? So the true course is a vector. Yikes. Is a vector that looks like, what do we got here? 7 to, I shouldn't be doing this in my head, 8.034 in the I direction. So 430.827 in the I direction plus 374.259 in the j direction. Ground speed. You're just finding the magnitude of that. It's not going to be the prettiest number you've ever seen in your life. Make sure you take the square root. 570.686. Notice how it ends up being a little bit more than the plane speed. We're adding to the plane speed. Our plane speed's gotten bigger. If they were pointing in truly opposite directions, you would expect to see a decrease in speed. But the wind is adding a little bit to the actual ground speed of our plane. And this is a number. This would be miles per hour. And my U hat would be, if I divided those out, so I would take the 430 and I would divide it by the 570. I would get 0.755 in the I direction plus the 374 divided by that same 570 number, 0.656 in the j direction. And that would be the heading. So again, we would see that's mostly even still because the wind speed was so less. So the wind did not really affect it too much. It did add a bunch to our speed, but the degree was so little and the speed overall was so little that didn't really affect our heading. Anyway, that's just your insight into the applications. I hope this made sense. I'll see you in the next one. We'll finally bring this into the 3D coordinate system. Thanks for watching. Bye.